Come rain or shine, hot or cold, the weather affects us all, every day. Something of a British obsession, the weather forecast is never too far away from the minds of nearly all of us. Perhaps because we want to know if we'll need an umbrella or not. Let's face it, the weather can change from dry and hot to a severe drenching in a matter of hours. But why? What makes this happen? We all know that hot air rises, and we also know what goes up must come down, and that's at the heart of everything to do with weather. The sun heats up the air, it rises, cools, then falls back down to Earth, creating our weather and airflow. But it can't be that simple, right? If it were, we'd all experience the same weather anywhere on Earth. So why is this not the case, and why do we have different and complex weather patterns? To find out, we need to look at all the factors affecting this rise and fall of air. Earth is surrounded by an atmosphere made up of gases and held in place by gravity. It's this atmosphere that protects us from the harmful bits of the sun's radiation, whilst also keeping Earth warm, a process known as the greenhouse effect. Earth's atmosphere is made up of 4 different layers. At about 500 kilometers above Earth, the outer layer, the thermosphere, is a protective shield, stopping harmful radiation. It's also the bit of the atmosphere where the International Space Station orbits. Beneath that is the mesosphere. This is the layer where most meteors burn up before getting to Earth. Next comes the stratosphere, the layer that converts the sun's UV rays into heat. Uniquely, this layer gets warmer the higher up you go. Finally, the troposphere. At about 10 kilometers above Earth, it acts as a canopy. This is where our weather happens. As hot air rises, it hits the ceiling and spreads out, cooling and then falling back down to Earth. It's these cycles that create the different weather we experience. The faster the air heats up, the quicker it rises. So we need to understand how Earth heats up to understand the airflow cycles. Okay, so it's the solar energy from the sun that heats up the planet. If we think of them as individual rays, each one arrives at Earth's atmosphere with the same amount of energy. However, at the poles, that energy is dispersed over a greater area than at the equator. Then, of course, you've got the distance the energy has to travel to reach the landmass once it enters the atmosphere, much further at the poles than at the equator. On top of that, you've got Earth's 23.5 degree tilt towards the sun, influencing where on Earth the energy is being concentrated. Of course, this is what gives us our seasons. The northern hemisphere points towards the heat source for the first half of the year, the southern hemisphere for the second. Let's take a look at what happens at the poles. With their snow and ice, along with thick cloud cover, they reflect a lot of the sun's energy back into space, further decreasing the energy that reaches the poles. In fact, any point greater than a 40-degree latitude, the outgoing heat radiation exceeds the incoming energy from the sun. Even with all these factors at play, if Earth was simply a landmass, we would have a relatively simple weather system. The flow of air, known as circulation cells, would rise at the equator where it is hottest, hit the ceiling of the mesosphere and flow to the poles where it would cool, sink and subsequently return to the equator. This would be nature's way of balancing the heat distribution and stopping the equator from getting ever hotter and the poles ever colder. But there are a couple more factors impacting this simple model. The first is our oceans. The landmass heats more quickly and by a greater degree than water, however, also cools more rapidly, whereas temperature fluctuations of water are much less, both day through night and season to season. All these fluctuations in heating and cooling disrupt the creation of a simple, single circulation cell, and a more complex 3-cell pattern starts to emerge. Either side of the equator are the Hadley cells, the mid-latitude cells next to those, and the polar cells top and tailing the globe. This creates 3 distinct bands in each hemisphere, each with its own circulation of heating, rising, cooling and falling air. You can think of them working like gears, working together as the air circulates. At high altitude, at the top of the troposphere, the cold airflow is moving between the cells, falling back to the surface between each one. This movement of air creates flows between each of the cells. Between the mid-latitude and Hadley cells are the subtropical jets, and the mid-latitude and polar cells, the polar fronts. As the circulation cells expand and contract, these streams of air meander around the globe, morphing and changing as Earth heats and cools. It's the subtropical jet between the Hadley and the mid-latitude cells that is commonly referred to as the jet stream, fast-flowing air from west to east. But it's the polar fronts that have the most profound effect on our weather. As the cells expand and contract, the polar front moves north and south. Behind the polar front is colder air, and as it pushes south, we experience more unsettled weather. Being the cold side of the polar front leads to some of the extreme wet weather we can experience, even in summer. The meeting points of the circulation cells create prevailing conditions. Where the cells come together, the air is either rising or falling. This creates constant areas of either high or low pressure. The cooler falling air are areas of high pressure, the warmer rising air, low pressure. At surface level, which, let's face it, is what we're interested in, as we can see from the circulation cells, the flow of air is from high pressure areas to low pressure areas. Low pressure areas are, of course, the rising, warm air. As the air is rising, the downward pressure is less, hence known as low pressure. As the warm air rises, it takes with it moisture from Earth, which forms clouds and ultimately falls as rain. High pressure is cooler, dry air falling back to Earth. Hence, high pressure areas are considered to bring good weather. In winter, this might mean dry, but usually means cold too. So I mentioned earlier that there were a couple more factors we had to consider, but only talked about one. Well, the other one is that whilst all this weather is happening in the atmosphere around Earth, at surface level, we are rotating underneath it. Let's take a look at how this affects everything that is going on. One of the easiest ways to see it is by throwing a ball. When thrown, it moves in a straight line. But if we throw the same ball from the same position whilst Earth is spinning, the ball appears to travel in an arc. This apparent bend is known as the Coriolis effect. This effect is also impacted by speed. If we mark a couple of spots on Earth, we can see that the Earth's rotation has a bigger impact at the equator. The further north or south you move, the slower the surface is moving underneath the atmosphere. If we bring back the high and low pressure bands formed by the circulation cells, and then add the flows at surface level, air flowing from areas of high pressure to areas of low pressure, introduce the rotation of Earth, and we can see how this impacts our experience of the wind at surface level, the Coriolis effect. This is why we have prevailing conditions. The easterlies in the middle of Earth, known as the trade winds, westerlies spanning the mid-latitude cells, and easterlies at the poles. If we go back to a flat map, we can also see the prevailing conditions created by the circulation cells having a profound impact on our climate. Whilst the bands of low and high pressure expand and contract over time, they remain relatively constant in the area of the globe they cover. It's no coincidence that the majority of the planet's rainforests are situated between the Hadley cells near the equator. The prevailing low pressure brings lots of rainfall. The majority of the world's deserts, including both poles, are situated on the bands of high pressure, where it's generally very dry. So what does this mean for us? Well, it's the constant movement, heating, cooling, rebalancing, and strive for equilibrium that causes the weather we experience, both at a global and local level. Although a complex chain reaction of events, there are some constants which are useful for our understanding of how the weather will affect us. Whilst there are many factors at play, at the heart of everything is the sun heating the planet. This is what drives all of our weather. No matter where we are, areas of high pressure are falling, cooler, more stable air. And of course, low pressure areas are warm, rising air carrying moisture, creating more unstable weather. We also know that at surface level, air flows from areas of high pressure to areas of low pressure. Of course, we know this as wind. Knowing these key things would definitely help us better understand and interpret weather forecasts and the weather we are experiencing.